So we've essentially finished our coverage of current lithium-ion batteries, and I will just finish with a few minutes talking about possible future developments. The first one is lithium-air batteries. Arguably, this is the holy grail of optimized energy storage. If you can have lithium metal anode instead of lithium graphite, for example, and lithium oxide as the discharge product instead of lithium cobalt oxide, so it's just lithium and oxygen, then you are going to get capacities that are almost as high as are theoretically possible. So there is a lot of research going on towards this possibility. It has to be said, it's still a long way from being developed commercially, and perhaps it will never be achieved. But if people don't try, then we will never know. So it's currently it's a hot topic in R&D in lithium battery materials. At present, there's most interest in a halfway reaction, which is lithium plus oxygen forming Li2O2, lithium peroxide, because this reaction is reversible. So we're not interested in just having a single primary battery. We want this to be reversible and rechargeable over many cycles. So the first stage, forming lithium peroxide, is reversible, but the second stage, forming Li2O, at least at present, is not reversible. And we have a table here showing the energies on a weight basis or on a volume basis for the two possibilities, lithium oxide and lithium peroxide, compared with the current lithium cobalt oxide battery. And the voltages are comparable. In fact, for the lithium oxygen are somewhat less than the lithium cobalt oxide, because the cobalt +4 oxidation state in lithium cobalt oxide is highly oxidizing and is more oxidizing than oxygen. But when you look at the capacities, they are significantly higher. So lithium going to Li2O would be 10 times higher on a weight basis than that of lithium cobalt oxide. So there's certainly, in terms of capacity, much interest in achieving a lithium air battery. But there are many problems with the materials. It's basically a material science problem that needs to be solved in getting suitable components that are stable and give reversible performance. So the cathode is usually a porous carbon black with a polymer binder, similar to current anodes in lithium batteries. We need a high surface area for the electrolyte contact. We need a location for the solid lithium peroxide discharge product. We need carbon for high electronic conductivity, and we need rapid diffusion of oxygen molecules so that they can come from the air to react at the electrolyte surface with the discharge, with the lithium ions from the discharge. And the electrolyte requirements, they need to be stable in contact with oxygen and with the discharge products. We need to have high lithium ion conductivity. We need a solvent for oxygen with high diffusion rates, and good wetting so that the reactions which occur at the electrode surfaces are rapid. So many possible electrolytes have been investigated, various organic salts, organic carbonates, and ethers. ionic liquids, and solid electrolytes. So many materials have been considered, but as yet none of them are satisfactory and give good performance over many charge-discharge cycles. So you will see in the literature lots of papers where people report results, but generally the cycling is pretty limited. And so there is the question whether they will ever become commercial. As well as lithium air, there's also significant interest in developing lithium sulfur batteries. And it could be that these will become commercial long before the lithium air ones. It's outside the scope of these lectures, but sodium sulfur batteries have been developed and are well established over the last 50 years. In fact, sodium sulfur batteries are used in power station load leveling applications, and so they can be made with megawatt size batteries. So certainly sodium sulfur, there are no problems with that. There are still issues in developing lithium sulfur batteries, but there's probably a better chance that they will be solved. The problems will be solved in the future. Second area, which has become of interest in the last 2 or 3 years and has suddenly become a hot topic in lithium battery materials development, and that concerns the oxygen in the oxides in the cathode. Because we normally think that oxygens are present as O2 minus ions, and any chemist will tell you, yeah, oxygen is O2 minus. But the question is it always O2 minus, or is it possible that the oxide ions can ionize? Can they liberate electrons to give, for example, O minus ions? Interesting question. And there is now evidence, a lot of good evidence, that this can happen under certain circumstances. So the redox active couple in lithium battery cathodes is usually the transition metal. And so we've seen the examples of cobalt 3+, 4+ in lithium cobalt oxide. There is nickel 2+, 4+ in this lithium nickel manganese oxide spinel. There is iron 2+, 3+ in the lithium iron phosphate. And the question then is, well, can O2 minus going to O minus also be a redox active component? So it's not a metal, but if we can get reversible redox activity of oxygen, then the advantages or the possibilities of this are that this can give rise to increased capacity in our cathode material. So if we have a cathode in which it has the redox active transition metal component, but as well as that, some of the oxygens of the cathode are also redox active, then in principle we can get enhanced capacity. And for about 15 or 20 years there have been examples known of materials in which the capacity is a so-called anomalous capacity, in that it's been possible to obtain charge-discharge capacities which are higher than theoretically possible from the content of the transition metal species. And so there's been evidence of anomalous behavior for quite a few years, but it's only recently been realized that actually, yes, oxygen is responsible, and that in fact we can have redox activity associated with oxygen as well as with the transition metals. And the particular materials that have demonstrated this effect are manganese-based, Li2MnO3 based materials, which are layered rock salt structures similar to the lithium cobalt oxide. The materials that have been looked at so far, although this is an ideal high capacity material, reversibility is problematic. And as shown at the bottom here, you can think of the oxygen redox process, O2 minus going to O minus and providing an electron. The problem is that the process doesn't stop at that point, because the O minus may well lose another electron, liberating oxygen gas. And one of the big problems in working with high voltage cathode materials is that they do lose oxygen readily during charge, and that changes the composition of the materials, and their electrochemical performance then is not good. So this is the problem, that if it's possible to utilize redox active oxygen, then you need to stop the process at O minus, because if you get the second half of the process going to oxygen gas, then that is bad news for the possible battery performance. Third area that people are interested in is high voltage batteries, and especially 5-volt batteries. And there have been examples of 5-volt battery cathodes known for nearly 20 years. They were discovered purely by accident, but they're now pretty well established. But the major problems with these concern the lifetimes. So when a battery is charged to 5 volts, that is an incredibly oxidizing battery, and so there are safety concerns and issues of compatibility between the electrode, the cathode in this highly charged state, and the electrolyte. And all the examples that have been tested so far, they do operate as shown in this graph here. You can get a plateau above 5 volts, but the lifetime of such materials during charge discharge is not high. So people are still working on this, and the problems may be solved in the future. Fourth area that is of current interest is on sulfur-based materials. Everything that we've been looking at in this course has been on oxides, but there are analogous sulfur-based materials, and there's a family of sulfides called thiolysicons. Lysicon was an early example of an ionically conducting lithium oxide material, which had interesting possibilities as a solid electrolyte. And more recently, there's been a family of sulfur-based analogues discovered, and so they're called thiolysicons. Lysicon is lithium superionic conductor. That's where the name came from. And so these are materials such as lithium germanium sulfide, lithium phosphorus sulfide systems, and here we have some conductivity data. So a typical conductivity, 2 times 10 to the minus 3 reciprocal ohm centimeters at room temperature. That's a pretty high conductivity. It's not as high as is theoretically possible. So a strong liquid electrolyte may be 10 to the minus 1 reciprocal ohm centimeters, but nevertheless this is a very high conductivity. And so such materials are being considered for thin film all solid state batteries with, for example, a lithium aluminium alloy as the anode, thiolysicon electrolyte, and then a sulfur based cathode material. A Chevreul phase is a complex sulfide rather than an oxide. So there's certainly developmental work going on, especially in Japan, on sulfur-based materials. Problems are, though, that they are air sensitive and moisture sensitive, so they're not easy to work with. You need glove box conditions to handle the samples. But who knows, in the future there may be commercial applications. Fifth topic is all solid state batteries. And again, this is a dream that many people are pursuing, because if you have an all solid state battery, you don't have any liquids, you don't have any problems of containment, containing your liquids. You can make them in various forms as thin films and so on. The problems are that to date there are very few materials that have high enough conductivity for use as an electrolyte. So you do need a very high conducting electrolyte for a start. That's one problem. Second problem, when you have solid electrolytes as well as solid electrodes and you stick them together, you have the problem of the interface between your solid components, and the interface will not be as nice and perfectly contacting as when you have a liquid as one of your components. And so there are serious interfacial problems in establishing low resistance contacts between your components. And then that becomes particularly important if there are volume changes during the battery operation. I mentioned earlier about the advantage of the lithium titanate spinel, where there are no volume changes on charge discharge. So that would be very appropriate for use in a solid state battery, because then that wouldn't have any deleterious effect on the anode electrolyte interface. So there are many problems still to be solved with all solid state batteries, but again, people are still working to try and solve them. And there is one small scale commercial example of a solid state lithium battery using a lithium phosphorus oxynitride glassy electrolyte. Its conductivity is not particularly high, but it's used as a thin film, and so the actual resistance of the electrolyte is quite small, with a thickness of 2 micrometers of the electrolyte. Its resistance is 100 ohms, and so it's feasible to use that in a battery. A final example is sodium batteries. In the last few years there has been an upsurge of interest in developing sodium batteries, and it has been realized that the intercalation processes that are used in lithium batteries can also be used in sodium analogues. The sodium ion is quite a lot bigger than the lithium ion, and originally people thought, well, you won't get easy intercalation reactions with sodium, but there are certainly examples where you can get quite nice charge-discharge reactions involving intercalation of sodium into the layered rock salt type cathodes. And so there's a lot of interest currently in developing sodium ion batteries. It has the advantage that sodium is very widely available. It occurs in seawater, salt in seawater, so it's abundant and it's cheap, compared with lithium, which is a rather expensive chemical, and you only find it in good deposits in certain countries of the world, especially in South America. So no predictions, but watch this space. I think we could see commercial sodium ion batteries in the fairly near future. And here are just 2 or 3 references that you can read more information on lithium batteries if you're interested. So that's the end of my course. I hope you found it interesting.